Hello out there, this is Nicole Hensoth, editor of HPC Wire, here with another in-depth interview session. So today we're going to be talking with Max Grossman from Rice University about improving accessibility of GPUs and other accelerators, including FPGAs, for a more mainstream class of software developers. Max is a researcher within the Habanero Multi-Core Research Group at Rice University and also a researcher at Repsol USA. He's spent the last 9 years focused on schedulers and programming models for heterogeneous and distributed systems, with an emphasis there on applications in geophysics, astrophysics, and medical imaging. Hey, Max.
Hey, Nicole. Great to be here.
Great to have you on. So this is an important topic that we're exploring today going forward because, while the promise of a rise in heterogeneous architectures might mean big performance gains for a much wider variety of market segments, the perception is that a lot of the languages that support these accelerators are too low level and have too steep of a learning curve to really find their way into more arenas. Do you think that that's a perception, a reality, a little bit of both?
I think it's a little bit of both. To some extent, it definitely depends on what your background is. If you're coming from working with exclusively Java or C#, obviously transitioning to a C and C++ API, as well as a lot of low-level CUDA or OpenCL API calls is going to be pretty difficult. I think for more systems-level programmers, it's an easier transition. There's a lot more analogies between working with GPUs and working with systems, low-level software. But there definitely is a steep learning curve, and it takes some time to get up to speed on these kind of GPU programming technologies.
Mm-hmm. And that includes also the other accelerators out there. So FPGAs, you're talking in your research, and we'll get to some of this in a second, about the wider array of accelerator tools, correct?
Yeah, and it's really exciting right now because a lot of different projects are coming out of AMD and Intel and NVIDIA with FPGAs, like you said, with GPUs, with putting GPUs and CPUs on a single chip, and a whole bunch of other crazy things with hundreds or thousands of cores getting stuck in a single processor.
Right. It is exciting stuff. To what level does that add extra complexity, or do you think that they're doing a good job of managing ease of use on the programming side with complexity and capability? Complexity and capability, rather.
You're definitely right. The tools are still building. It's kind of analogous to where programming was, 30 years ago, 20 years ago, when we just had C and Fortran, and we're still building towards more higher-level programming languages like Java or C# or other options that are out there now. So as these new architectures come out, we kind of have to move towards some new programming languages or models that map well to the hardware. And I agree that we're not there yet, and it's still something in very much a research stage.
Okay. So what's missing there that's around the bend in terms of possibility? What do you need that's there on the ease of use side that is coming? What's most important?
Well, obviously I think if I knew the exact answer to that, it would have been implemented. But I think definitely the tools need improvement. To some extent, this kind of the hardware needs to kind of get out into the mainstream where developers can actually build the tools and build out the programming languages and models. To a big extent, it is still very much a specialized area in research in academia and industry, and it really isn't being used by your everyday programmer who's just working on some web software, things like that. And if that doesn't happen, there isn't going to necessarily be a market demand to make these technologies more usable.
Okay. So your advice for the Intels, NVIDIAs, and AMDs is send more free hardware. Is that
Yes, send more free hardware to Max Grossman specifically. But
okay, very good. So I'm curious here. I know that a lot of the vendors who have these products have made significant, admirable efforts to make this more accessible. So if you want to call out a couple of those efforts and talk about where they're good and where they're still falling short in terms of appealing to a wider class of developers, that would be great.
Sure. So I guess the first one that probably pops to mind is OpenACC, which is kind of analogous to OpenMP. You add some pragmas to your application, and the idea is that parallel for loops automatically get mapped down to CUDA or OpenCL API calls. And so I would say that that's probably gotten the most attention recently because it's a very easy transition for people who are already in HPC or already doing parallel programming and are therefore already familiar with OpenMP to then switch over to OpenACC. It still is fairly low level. The problem with abstractions like this is that once you add them, you then lose some of the control over the hardware. You lose some of those performance benefits. And so I think it's kind of a balancing act, because if you're going for GPUs, FPGAs, or any of these new architectures, the reason you're trying that is because you need high performance. But then if you go for a high-level programming model or programming language, generally the trade-off is that you lose some of that performance that you're trying for. So,
right.
To some extent, the implementation of these high-level programming models is, kind of going against the whole point of these architectures. It's kind of cutting off some of those benefits.
Right.
So
quite a catch-22. Right?
Yeah, exactly. We want them to be more programmable, but what's the point if we're then just making them the same performance as your everyday multi-core quad-core CPU?
Yeah.
So in terms of other efforts, there's been recently a lot of interest in mapping code executing in the JVM written in Java down to this heterogeneous hardware. And usually the route is to auto-convert JVM bytecode into OpenCL kernels. And so a couple of big projects there are Aparapi, Root Beer from University of Syracuse, and the project Sumatra in the OpenJDK project. And all of these are kind of taking similar approaches and kind of building off of each other in terms of generating OpenCL kernels at compile time or runtime based on JVM bytecode. But the high level is that a lot of programmers are familiar with Java already, and so what we want to do is we want to give those high-level programming languages a little bit of extra oomph when it comes to computational kernels. And of course, the problem then becomes doing this efficiently and doing it in a way that doesn't get in the way of the Java developers, so that they continue to have their high-level abstractions, but they also get high performance.
So let's get over to your research, and one of the reasons why you and I connected, I think that what you're working on is interesting and representative of a lot of the projects you just mentioned. So I know that you are working on moving Java and more common high-level languages to extend over to widen this group of potential developers. Can you describe in depth what it is that you and your team at Rice are doing?
Sure. So my research group at Rice, one of our main focuses of research is the Habanero Java parallel programming language, which is a language extension and a runtime extension to the JVM and a Java programming language, which adds some parallel programming intrinsics. So you get things like parallel for loops and asynchronous task creation and data-driven parallelism. So one way to build on that is to take these parallel for loops and basically use them as hints from the programmer that says, this parallel for loops, all these iterations are independent of each other. There's no data races. I am, telling the compiler exactly what this program is doing to some extent. And we can use those hints to map Java programs onto OpenCL hardware. So if they express a parallel for loop, we can automatically assume this can be safely executed on the GPU or the CPU. So it's kind of cheating to some extent because, we're using some hints from the programmer, but it allows us to remove the concerns from the programmer, like writing a lot of glue code, writing code to get data from the Java heap into the C++ native code, which can then call into OpenCL and copy that data to the OpenCL device. So there's a lot of code being automatically generated, and there's also the generation of the OpenCL kernels themselves from the Java bytecode. that we're taking care of. And so this is just taking a lot of burden off of the programmer and allowing them to use this powerful hardware from a fairly high-level language.
Okay. And who do you expect to reach? I'm not sure exactly what your plans are with this research project. I imagine you'll try to push it out and get people to use it, correct? And if so, who are the people you're targeting with this?
Well, I think it would be great if people would use it. I don't know if we have any plans to actually target any specific developers or any specific projects. I think anyone who's already using Java and needs some help on the performance of parallel code sections could benefit from this. This could be people writing web apps that are doing cryptography. This could be people writing web apps that are doing machine learning, or really anything in Java where the Java threads running the JVM is your bottleneck, and to improve latency, to improve throughput, you think running in native code is what's right for you.
Okay.
We don't have any plans to extend, to release this out to the industry at the moment. But there are other open source projects like Operapi or Rootbeer that are accessible right now. You can go download the source code and play around with it.
To go back to that one in particular, how does what you're doing then compare to a project like that? Where are your own strengths and weaknesses comparatively?
So our project at Rice is actually built on top of Operapi. Operapi provides a lot of useful tools, as does Rootbeer. They're both very similar projects. They provide tools like the JVM translation or the JVM bytecode translation to OpenCL kernels, as well as auto-generating some glue code or providing an API that calls into native code, which then copies objects to the device. So we're actually building on top of these and kind of taking advantage of the work that's already been done, but providing kind of integrating with the Java language to a greater extent. So usually with these, you kind of have to have some kind of kludgy code, declare some extra objects, or add some extra workarounds in order to take an existing application and put it on top of Rootbeer or Operapi. And so we're kind of adding some programming language extensions, which make it a little bit easier. But we're also using it as a research platform to take a look at, where can we really push this limit. So, for instance, a very recent paper that we put out took a look at using speculative execution in the JVM to catch any exceptions while running the computationally intense part on a OpenCL device. So what you get here is you continue to get the guaranteed exception semantics of the Java programming language, which are very useful in case you happen to have a bounds axis or divide by zero. But we're also getting the computational benefit of running on an OpenCL device. So to some extent, this is a research platform for us, and we're really trying to push the bounds of what people have done with hybrid JVM and OpenCL execution. But we're also trying to build on top of these existing projects because we don't want to reinvent the wheel.
Right. That's exciting. Let's kind of move back higher level here for just a second. For people that maybe are not programmers, or if they are already using some of these OpenCL CUDA languages and they're already in that world, what do trends toward making these accelerators more accessible? What does that mean beyond the realm of scientific computing, where you most often see the use of GPU acceleration and such? What do you see happening in this general space?
It's a very good question. So in general, we're going to be seeing increase, even if you're still using CPUs, you're going to be seeing an increase in core counts. You're going to be seeing some pretty significant changes, I think, to the architecture that you get in your everyday server platform or your laptop. So to some extent, we're seeing right now that GPUs and CPUs are kind of coming together and beginning to meet in the middle. GPUs are becoming more general purpose. They're getting larger caches. And we're also seeing both the GPUs and CPUs being put onto a single chip, so you can take advantage of both at the same time. I think that even if you're not in scientific computing, even if you're not in high-performance computing, you're going to be seeing architectures coming out and being very mainstream that are maybe not to the same degree as GPUs are in terms of their parallelism quite yet, but you're definitely going to be seeing a lot of the same problems in terms of data movement, in terms of structuring your code efficiently for optimal performance in these new architectures. And I'm sure people in the industry are working hard to make that as little a problem as possible and to develop tools as much as possible. But solving these problems or working on these problems for GPUs definitely extends and applies to the kind of new architectures that we're going to be seeing coming out in more mainstream applications and in more mainstream platforms, hardware platforms for developers.
Right. Do you think on the ease of use, the accessibility level in particular, since that's the point that we're coming from, is there advantage to having a discrete GPU over having everything on the same die? Do you see them all going toward the same die? What do you see happening there?
For accessibility?
For mainstream use.
For mainstream use, yeah. So I guess the main advantage of having both processes on the same die is that oftentimes you also get a shared physical memory. And that helps programmability in that the software developer doesn't have to worry about transferring data from one physically separate memory to another physically separate memory. Current implementations oftentimes still have separate address spaces, but it's the same physical memory. So from an accessibility point of view, the programmability becomes a little bit easier with both processes on the same die just because they have this shared physical memory, and you can have each device accessing the same memory locations without any transfers or copies. And that's great from a performance perspective as well. So of course, with both chips on the same die, generally you get like a slightly less powerful CPU and a slightly less powerful GPU. So I think these are, for the moment, are mostly, you're only seeing these kind of chips in laptops or tablets where energy consumption is a very important factor. And so you get better energy improvements from this.
Interesting. Well, Max, your insights have been very valuable. Thanks for telling us about your research, and keep us up to date with what you're working on next.
Yeah, thanks for talking with me.
Sure, thanks.